Okay, hello and welcome to the final video of this series. In this, I want to discuss the solution for part 4 and 5 together because they are similar. So let's go ahead and understand this challenge. So this is the efficient broadcast challenge part 1. In this challenge, we'll improve on our fault tolerance, which was the previous challenge implementation. So they have defined some metrics for success for this challenge, and not only those metrics need to be met, but the overall correctness of the distributed system also needs to be checked. So let's go to the specification. In this challenge we have 25 nodes in our cluster, and each client server communication has been added a delay of 100 milliseconds to simulate geographic latencies or a busy network. So this is the expected outcome for the constraints that they are expecting. So messages per operation should be below 30, and median latency is below 400 milliseconds. Maximum is below 600. They are also telling to ignore the given topology if it's not giving you the expected results. So this messages per operation field is present in the results. So as we saw in the previous challenges as well, so we are going to receive this output format where clients and servers message counts are displayed. So this is the number of messages that were passed between servers, internal messages, and these were the messages that were sent between client and server. So as you can see, this message count is really high as compared to the client messages. Okay, and the next one is stable latencies. I also explained this in the previous one. So this is the maximum latency, this is the median, and these are the 95 and 99 percentiles, which needs to be below these given constraints. And this is the test command. So we are running 25 nodes this time at the rate of 100 messages per second with a latency delay of 100 milliseconds. Let's also check the part 2. Part 2 is almost same. We just these constraints are different. So earlier it was 30, so now they are expecting the messages per operation to be below 20, and the median and the maximum latency below 1 and 2 respectively. Okay, let's go ahead and understand this challenge, and let's find some ways to approach this. Okay, so the main idea is to reduce the number of inter-node messages and the latency. The latency in this case measured using the delay between a broadcast message and a read message sent by a client, and expecting the same output which was sent by the broadcast message. So since we are handling our distributed system using eventual consistency, this latency is defined using those difference of time when a client asks us to broadcast a message and the time when it actually receives that message again. And these were the constraints that were given in this challenge for part 1 and this for part 2. So assume that we are building a single solution for both of these parts. So we will assume that messages per operation should be below 20. So below 30 and 20 is same as making it below 20, and these latencies will be below 400 and 600 respectively, because the part 2 expects a larger latencies, and we are going to create a single solution for both of them. Now let's understand the topologies. So the first item that we did at solving this, we were sending messages for each broadcast message to every other node in the cluster. So this topology that we used was fully connected. That means each server can communicate with any other server in that cluster. So let's go over the metrics that, or we can say the expected latencies and the messages per operation that will be the result of if we follow this topology. So we have 25 nodes in this challenge, and let's say on some broadcast message on a certain node, we set internal message to all the other nodes in the cluster. So for n nodes, if each of them receives a broadcast message, we end up sending n times n minus 1 messages in total, which is around 600. Um and this is quite large, and we cannot just simply send this many messages each time an operation comes. So let's go ahead and check the second attempt or second solution that we can think of. So in the fault tolerance broadcast challenge, we used batches instead of sending uh, these messages all at once and blocking the incoming requests. We will send them in batches of 50 or 100 and mm, perform those internal message transfers in some frequent intervals. So what we can do is, instead of sending internal messages after receiving some message from the client, we use batches to send internal message after frequent intervals. So let's say after every 500 millisecond we are going to send the required message to all the other nodes in the cluster, and this will reduce the number of messages per operation significantly, because let's say our delay is 500 millisecond. In that 500 millisecond, uh, hundreds or even thousands of broadcast message will come to that node. So overall, if we average out the number of messages, internal messages, it will be reduced. Um Still, the concern is that the latency is still very high for this, because let's say some node is sending, let's say this node is sending message, it waits 500 milliseconds. In the next batch again it is going to wait 500 milliseconds so that that value is transferred to some other node, and maybe this node is currently network, this node has a network partition between them, so the net latency will be increased, or it is not possible to achieve below 400 millisecond latency in that case, depending on the interval limit that you choose. Now let's try to change this topology for a moment. So let's assume we are using star topology. We have 25 nodes and we are considering node n0 as the center of the star topology and all the other nodes surrounding it, and this edge denotes two-way communication between nodes n1 and n0. So n0 can send message to n1 and n1 can send message to n0. So if we consider this topology and assume that each node waits 100 millisecond to send a message from its cluster, from its node to the node n0, we can make some observations. So if we have a batch, each batch waits let's say 500 millisecond to send a message, all the message that it has, and it is going to send them. What we arrive at is node send is going to send 24 messages per batch because it has 24 neighbors in its cluster, and all the other nodes have only one node in its cluster to communicate with. So the overall messages is reduced drastically, because 24 nodes are going to send only one message and one of them is going to send 24 messages. So overall you can say in a particular batch we are sending only 48 messages. And this might, so the messages for operation is an averaged out quantity, so the results may be different based on what all parameters we are going to use. But this approach is definitely going to reduce the latency as well as number of messages per operation. One more thing to note here is any two nodes are at distance at most 2 in this topology. So the farthest distance between any two nodes is the edges that we need to be traversed is at most 2. So latency will also reduce, because even in case of network partitions there will be at most one or two internal messages that needs to be correctly transferred, so that the value is updated and consistent across the entire cluster. So let's say for example N4 wants to send, or N4 wants to update all the nodes in the cluster, and let's say how that value propagates to N2. So N4 wants to send some value, let's say 10. It is going to send it in 100 milliseconds to node N0, and node N0 will send it in 100 milliseconds to node N2. This 100 millisecond is a user defined quantity, or we can change and alter this and experiment how what type of results are achieved by changing these two parameters. Okay, so this was the main idea behind this. So the final solution is to take the same solution which is from the fault tolerant broadcast implementation, and to use batch gossip messages every X milliseconds. We already used this in the fault tolerant broadcast implementation and changed the topology to star topology. In the previous implementation we used the fully connected topology. You just need to use the star topology in our case now. So that's all about the observations and the insights with this problem. Let's go ahead with the code. Okay, so the message object remains same. We have the same body types that are given from the client: init, broadcast, read, or topology. We are going to ignore the topologies that they are giving us, or you can even try checking what all results are achieved using their topology or star topology. Next is the internal message, which is the same. We are sending all the message in the current node in an internal message. This thing we saw earlier, we need to have two references. One goes to the secondary thread and one goes to the main thread. We are in this code, we are processing the init message. We are extracting out what is the node ID of current node and the all the nodes in the cluster. We don't need that because we already know we have nodes numbered from N0, N1 up to N24. Okay, so that's it, and I have again used a channel here to send the topology from the main thread to the secondary thread. I will also, so this is the reference to that. So here we are creating our star topology. So if the current node is N0, the adjacent elements to it are N1, N2 up to N24. So this code will generate the topology and send it to this secondary thread, which receives the topology. As you can see here, it is going to receive the adjacency list initially. It is, so this thread is spawned first. It is going to accept and receive the topology from the main thread that we are generating here. This is the star topology implementation, and now it is going to start the batch processes, which is I have considered the frequency here as 150 milliseconds, and after every 150 millisecond it is going to go through all the nodes in the adjacency list of the current node, and it is going to send those messages, which is the same thing that we saw earlier. So in the from the fault tolerant broadcast implementation, only the thing that has changed is the adjacency list has been changed. Initially it was all the nodes in the cluster nodes. So the thing I have commented out here, this we used here, we went through all the nodes in the cluster nodes, but now we are changing the adjacency list. We are using star topology here. All the implementation remains same. We are printing it to the standard output here. Init message we are already processing here to extract out the node ID. Now the broadcast message, we are not going to send any, we are not going to invoke any internal message after a broadcast message is received. We are spawning a separate thread which is running an infinite loop every 150 millisecond. It is going to inform all the other nodes in the cluster. So the way this is also fault tolerant is because we are sending all the messages. So as you can see, this secondary is a reference, a mutable reference, which is a mutex to a hash set. So for the data in this hash set, we have created two references, one for the main thread and second for the secondary thread. So for printing it to the standard output, we are locking the reference and cloning it and sending the messages in the internal message. So, and whenever an internal message occurs, we are going to extend our hash set with the messages that were received. This way, even if in case of network partition, even if a value is not propagated initially in the later internal messages, it will be shown or extended in the current nodes messages. Okay, so that's it for the implementation. Let's also go through the results. I've run this already. I will show the results, then messages and logs. So this is a little messy because the number of nodes are very large. So as you can see, this black colored lines are the internal messages. They are taking too much time, but they are working concurrently one after the other, and all this read and read OK messages are also getting transferred. So this internal messages are being transferred after every 500 or 150 millisecond, sorry. So as you can see, these are the messages that are being transferred. Okay, so about the result, they expected us to give a latency of 400 millisecond, median latency of 400 millisecond, and we have achieved 189 and maximum as 363. So this is acceptable. And the next one is messages per operation. So as you can see, the client has sent 4112 messages and all of them were received, and in between servers we have sent around 9886 messages, out of which 9865 went through and other ones were dropped because of network partition, and the overall value for messages per operation is quite low in this case because we have used batching for sending internal messages. So this value are significantly very less as compared to what they were expecting. Okay, so for the logs, it is very large. As you can see, the output. Yeah, that's it for this. I guess most of the, it was And this challenge was all about making changes in the topology and building the solution from the previous implementation and experimenting with some parameters as well. So it is not something fixed that a particular value is going to give us the expected output. So you can experiment with this value, or even a certain optimization that you can perform is you need to store what all values other nodes in the cluster know. So instead of just storing a hash set, you also store 24 other hash sets which denote the values that are present in the other nodes, and you only send those values instead of sending all these messages. So this is clearly unoptimal. We can perform some optimizations and reduce the number of operations or the latencies even to even lesser amount. So that's it for this video. If you like this series, do share among your friends, and do try this challenge on your own and in your own programming language, that whatever programming language you use. Yeah.